Hi, I'm Catherine Amstead, and this is my lab report on constant velocity. The purpose of this lab is to analyze the motion of an object on the x-axis moving at constant velocity, and then to create a computational model based off of Newton's second law. Following that, I compared the observed data with the data from the computational model and found that the slopes of the observed and predicted lines are almost identical when time is closer to zero, but as time went on, they diverged. The observed slope decreased while the expected slope remained constant. Some fundamental principles adjacent to this experiment are Newton's first law of motion. An object in motion will stay in motion at a constant velocity, and an object at rest will stay at rest unless acted upon by a force. There's also Newton's second law of motion, which is that force is equal to mass times acceleration, and that can be used to derive the velocity update and position update formula, both of which are central to our computational model. Speaking of models, our experimental model used tracker. We first took a video of an object moving along a flat surface and included a meter stick as reference, and that's that blue line there. I then created a coordinate axis and oriented it so the object can move along it. That is the pink axis, and track the position over time using those red dots. Computational model was done using GlowScript, and it involved iteration, which is predicting the motion of an object in small repeated steps. I found the net force, updated the velocity using the velocity update formula, used that new velocity to update the position using the position update formula, changed delta t just a little bit, and repeated the whole process. So let's talk about the experiment itself. The system for this experiment was a whiteboard eraser, and the surrounding is every object in the environment that interacts with said eraser. Some initial conditions are the mass of the eraser, which is 0.301 kilograms, its initial position, which I got from that coordinate axis and tracker in the previous slide, which is 0.000979 meters for the x component and 0 for the y and z components respectively. The initial velocity, which I found by taking the average velocity of the first 2 points, those first 2 red dots in tracker, is 2.39 meters per second for the x coordinate. And our initial time, of course, is t is equal to 0. This is our experimental video. For our computational model, the first part of the code wasn't changed at all, and this is just to play around with the color of the ball used in that model, that illustration, and the color, the size, etc. The initial conditions here had to be updated with the initial conditions of our experiment, such as the mass of the, well, not the ball, the eraser in kilograms, the initial position vector, the initial velocity vector, and then the change in time for each step, because change in time on the computational model needs to be equal to the change in time it was in tracker. This loop here is used to calculate the position and the velocity. We have, while time is less than 0.633, because that is the last measured time in tracker, we have the net force calculation. The net force is always going to be equal to 0, because it's mass times acceleration. We have a constant velocity. Acceleration is the derivative of the velocity. Derivative of the constant is 0. Net force will always be 0. And that means that for our velocity update formula, that last term will also always be 0, indicating, again, we have constant velocity. The position update formula will occur every time we go through this loop. As t changes, so will the position of the eraser. And here are the results. As I said, the position increases over time, and that just means that the eraser moves along the positive x-axis. Here's the spherical computational model, and the velocity does not change. When you compare these two results, you can see that they're much closer when time is closer to 0, and as time increases, the observed slope decreases while the predicted slope continues to be the same because that's a constant velocity. Why are the predicted and observed results different? They're different because the computational model assumes that there are no forces acting on the eraser of the experiment, and that net force just equals 0. But we know that there are forces acting on the eraser experiment. And because a change in the net force leads to a change in velocity over time, as you can see by these two equations, as time increases, the velocity of our experimental model is going to change, and as such, the difference between the two lines will become more pronounced. So what if the axes were flipped? First of all, the speed, the magnitude of our velocity would remain constant, but the direction would change, and therefore the velocity would be changed. Now the velocity would still be constant, but instead of being constantly positive, it will be constantly negative. And that's because the axes were set so that the eraser moves in the positive x direction. If the eraser were now moving in the negative x direction, it would result in negative position values, creating a slope in the negative y direction. Is it possible to say how many forces are added together to give net zero force? No, because there are too many forces in the situation. Just from what we learned in class, we know there's friction acting against the movement of the object. There's gravity pulling down. There's gravity also from every object, not just Earth's gravity. And then there's force in the hand that creates our initial velocity. In conclusion, we analyzed the motion of an object along the x-axis with constant velocity using both a computational model and an experimental model. We used Newton's first and second laws to understand and calculate position change at constant velocity and looked at how real-life situations can differ from textbook problems in terms